Okay, this is part 4 of DG vector bundles chapter. So let's go. The first proposition is again the smoothness criterion for sections using the language of frames. So let's start with the local frame. Local frame on U of f, which forms a frame of V on U. Then a section T U to V restricted to U is smooth if and only if there exists if and only if there exists a1 to an in C infinity U such that T equals to a1 plus an. Okay. One person and the local collection of local sections of local sections of V and U. Then a section T is smooth if and only if this is the C infinity function such that T is actually S. Okay, the proof is quite easy. So what we consider the local trivialization, right? Consider the local trivialization H from U cross RK Rn to V restricted to U, basically pi inverse U. Then H of P comma C equals to 1 to n I S underscore I of P because psi is a frame and one can write note that section from U to U RK, U to U times RK is given by S of P equals to P comma A1 of P comma A n of P n of P So the in section T of U to V where U is given by H circ S P equals to T of P implies S and the above result to show smoothness section and Now let's start a very interesting topic. Again, another interesting topic. It is called the vector field. So vector fields. So these are basically sections on tangent bundles, right? So let M be a smooth manifold. So vector field on M is a section of Tm. A vector field x m Tm is called smooth if it is a smooth. If it is a smooth section. We denote the set of all smooth sections on Tm. We denote set of all vector fields. Vector fields on M as mf x m equals to gamma of Tm. Well, that is a okay. So yeah, these are very natural things to discuss, occur in nature and all of that. So some examples. One, what is a vector field on Rn, if you want to ask? Then basically we know that Trn is isomorphic to Rn times Rn as vector bundles. We discussed about that. And if x to Trn is a vector field x of p equals to p comma v of p, where is simply V in C infinity R2 to R2 है ना. This is sort of cool. I mean, yeah. This is only the sort of cool vector field. Okay, similarly you can define like R into Rn functions, right? So you can generate another called gradient vector fields. Vector field if f Rn to R is a infinity Rn function define block f equals to frac p partial x1 call the image. Hello, back. So I just paused the recording, and it was Prag's birthday. It is Prag's birthday, so we did some cake cutting. Okay, so our next example is okay. Mm-hmm. Okay. Our next example is based on the fact that if M is a regular submanifold of Rn, then the tangent bundle of the manifold M will be a regular submanifold of Rn cross Rn. So example 5, slide 5, and then we'll consider some of the regular submanifolds of Rn and see their tangent bundles and see the vector fields on the tangent bundles of such regular submanifolds of Rn. So okay, before that we'll just make a few remarks on the before, yeah. So let's consider such vector manifolds and see what the vector fields are. We'll realize few things. So 5, let's just say 5. If M is a regular submanifold of Rn, regular submanifold, then Tm Trn is a regular submanifold. Is a regular submanifold. Now, if X M to Tm is a vector field, then X gives us a smooth function X of P equals to P comma V of P. Now where V is indeed in Rn, but it belongs to a tangent space. It's not, yeah. Where V in C infinity of M comma Rn and V of P in TPM. So what we are saying is X is a vector field, then X gives us a smooth function X of P, where V is C infinity M comma Rn and V of P is in the tangent space of yeah, I see. Yeah, V of P has to be in the tangent space of M, which is in Rn, because it's embedded in it. It's a tangent space of TP. Yeah, it's a subspace of Rn, TPRn. So yeah. Now basically problem set x m to tm is a vector is a field, and x gives us a smooth function x of p equals p comma v of p, where v is in c into tm comma r and v of p is in tp. So as you can hear, there is a lot of jetney noise as usual. Just too much. So from the problem set, Sir quotes that if M is a regular submanifold of N and f k to N is a smooth map where f of k is in M, then f k to M is smooth. So how is it relevant here? Hence vector fields on M are given by smooth function M to Rn. Such that V of P belongs to TPM for all P belongs to M. So the statement is that vector fields on M are given by smooth functions Vm to Rn such that V of P in TPM for all P in M. That's the general theory that we want to say. Smooth functions we use. Okay. It's isomorphic to Rn, but it's not in Rn. For general manifold, this is not true. Yeah. This is V of P is in Rn only for these regular submanifolds of Rn, right? In general, there's something else that we're probably getting into the next lecture. Yeah. So now let's actually consider let's look at some examples. Consider S1 a regular submanifold of R2 and x y minus 5x. So yeah, we see that the vector field on S1 given by minus y comma x doesn't vanish anywhere, and it's in fact it's a the tangent space is actually one dimensional. The fibers are one dimensional vector spaces TPS1 for all p. Then so is a rank 1 vector bundle um, rank 1 vector bundle x is being non-zero is a frame of TS1 implies indeed implies TS1 is the trivial vector bundle TS1 cross R is isomorphic to S1 cross R. The closed manifold of R2 and Sx equals to cap x1. We see that. Is the trivial vector bundle? Time for another image. So yeah, S1VF dot JPG vector field on S1 non-vanishing vector field on S1 which is a global frame on TS1 global frame on TS1 yeah, and just a one-dimensional subspace. So this is yeah. So this is non-trivial. That I mean, TS1 is as a trivial bundle is not a general. TSN need not be a generally trivial bundle. For example, TS2 TS2 is also a trivial vector bundle, right? Isn't it not? TS2. Sure. This is interesting. TS2 is not a vector bundle. This is not a trivial vector bundle. Yeah, in fact, this is a very interesting that you're talking about vector fields, and you're getting information about the tangent space. In fact, as we'll see, there is a isomorphism between the set of all vector fields on a manifold and the derivations on it, which is basically identified as a tangent space, right? So it gives you the relation, it gives out the how the tangent space is, and then which is exactly the you'll get the through that you can just see the trivial, if it's trivial vector bundle, if the tangent bundle is trivial or not in that case. Yeah. In TS for S1 apparently the tangent space is trivial. For S2 I could assume that at every point there are tangent planes. It looks like all the TSNs are trivial. So is trivial. Why is TS2 non-trivial? Acha. What? Oh. Oh, yeah, 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 yeah. Oh, yeah, 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 yeah. What do you mean by the tangent space? The tangent space at each point is indeed Rn. That is not the problem. The problem is it locally trivializable? Is it parallelizable? So that's what the term is parallelizable. Thing is that can you comb the? I mean, sorry. Can you? Okay, yeah, yeah, yeah. Can you globally define? Can you globally define a frame exactly? That's the basic essence of all. Can you globally define a frame over all this surface? Okay, apparently in TS1 you can, which is precisely the vector field minus y comma x is a global frame because it doesn't vanish anywhere. So one way to look for the fact that TS one is a trivial vector bundle. Trivial bundles is actually non-trivial. It is not true that any TSN is trivial. On S1, TS1 being a line bundle and the above x being a non-vanishing vector field at the above x being a non-vanishing vector field and above x a non-vanishing vector field gave us a local frame. So gave us a global frame such that the entire tangent bundle is actually trivial. Indeed, at any point on S1, the fibers are R1, but it is non-trivial that it's non-trivial that there is that TS1 is globally trivial. Indeed, at any point on S1, fibers are R1, but it is non-trivial that TS1 is globally trivial. TS1 being TS1 being TS1 being a line bundle and above X, a non-vanishing vector field gives a global frame such that the entire tangent bundle is actually bundle is trivialized, or formally called parallelizable. It is not true that any TSN is trivial. hints towards non-vanishing vector fields, towards importance of non-vanishing vector fields and obvious importance. Global frames. Important to note the existence the non-vanishing vector fields. It is true. It is not true that in fact the scene is parallelizable only for equals to 1, 3, 7. We note that non-vanishing vector fields. We note that non-vanishing vector fields. We note that the non-vanishing vector fields are important to analyze the parallelizability of manifolds and frames, global frame. This is a global frame. Global frame. Okay. In fact, any group, any tangent bundle of any Lie group is trivial. S2 subset of R3 consider X Z equals to minus Y comma X comma 0. Exactly, it was important that it belongs to, in fact, X comma Y comma Z perpendicular orthogonal single analytic. But interesting, makes sense. Verb. Cool. Cool. So we are considering S2 now, and we'll make important remarks actually. Consider S2 and consider X R3 TPS2 P belongs to XYZ. So okay. Okay. So the vector fields on this clearly vanish when x comma y comma 0 and z is anything. So basically North Pole and South Pole, this vector field vanishes. So clearly when it vanishes at such points, it cannot be a global frame. No? Clearly it cannot be a global frame. That. So in fact, so yeah, in fact it is connected to the topology of vector field is this vector field vanishes at the north and south pole. The south poles at the north and south poles. South poles. And in fact, this is related to the topology of S2. In fact, this is related to the topology of S2. S2. The Euler characteristic of equals to 2. Film. Okay, this is an interesting lecture. Talked about vector fields of manifolds. In fact, very interesting case is that you can talk about vector fields easily when you have the tangent space of the manifold in the tangent bundle is a subspace of Rn, so your elements of the tangent space are in Rn, so the vector fields are basically given by the functions from the manifold to Rn. This is possible because the manifold is itself a submanifold of Rn, and then the tangent bundle of it follows that the tangent bundle of the manifold is a regular submanifold of Rn cross Rn. So we have seen few examples for S1 submanifold of Rn and S2 submanifold of R3. S1 is submanifold of R2. So yeah, and yeah, I do appreciate now that TS2, we did talk about TS2 in the last lecture, right? And we talked about that it's a vector bundle, and that now we are discussing something about it. It's non-trivial apparently. It's non-trivial vector bundle. It's not a trivial vector bundle, and yeah. Okay, so yeah, and also vector fields give, okay, I mean this vector field is essentially a rotation. So rotation of S2. In fact, vector fields give nice diffeomorphisms on manifold. Yeah, so this field is essentially a rotation of S2. In fact, vector fields give nice diffeomorphisms of the manifold. And yeah, we will see next through integral curves and one parameter group of diffeomorphisms of the manifold through such integral curves. Integral curves are basically curves satisfying their derivatives as these vector fields, right? Very interesting stuff. So there it goes. Now we are in last lecture of week 6, where we look at more properties of vector fields and interesting stuff here also, right? Yeah. So this will be part 4 done. Yeah, cool.